Take a paper towel or something so your hand doesn't get filthy.
On. I'm not going to be eating yet until after the stream. Paige, she got some sort of wrapper.
Hey, what are you doing?
I love you.
Please stay here for a minute.
Okay.
Hey, stay.
Good morning, everybody. Just gonna wait a few more minutes to see if anyone else shows up before we begin. Paige, come over here. Come on. Yeah. She went to the bedroom looking for you. She was confused. on. So we're going to go ahead and try to start something today. You folks that are in here, if you don't mind just saying hi in the chat so I can actually know who you are. And I can actually, once again, get to answer your questions a little bit more. So if you guys would just be so kind and just say hi, tell me who you are. Good morning, Kevin. Good morning, Krishi. Okay. Good morning, Akshay. So we're going to get started today. Coffee. It's hot. Sorry about that. We're going to get started this morning. We're basically at the end of the chapter for waves. There's a few things that we've been talking about at this point. Obviously, we know the generic wavelength, frequency. Wait, did I just say frequency twice? Wavelength, frequency, wave velocity. You guys remember how to find the tension and constructive interference. Once again, constructive is when the parts of the wave add together. Destructive interference is when the waves cancel each other out. And it constructs an area where it destructs each other. Those areas of constructive interference are called antinodes. And those areas where it's destructive, we call nodes. And those are the key things about that. But there's another principle of waves we haven't talked about yet, and that's what happens if the waves that are coming in, if they are different frequencies or wavelengths, because they're interchangeable words. Can you guys see this whiteboard? Can you guys see it? It's blank right now. There's nothing on here. A little bit. Okay. Well, I'm going to use big markers. So imagine if you have a wave like so. Okay. And let's imagine you have a second wave. Like so. Okay. And I tried to draw it correctly so that here, if this is one wave, this here, 1, 2, 3. I drew 3 waves in this picture over here. So if you think about the interference where they would actually meet and get bigger, it looks like something like this here. This would be a big area. This kind of is a big area. This kind of is a big area, but it's not perfect. So you could see how even though there's crests, troughs, and troughs, it doesn't overlap 100%. And even I could see, though, right here, this is definitely a constructive interference there. It's the same pieces in the same spots. Here's an, I'll do that in green, actually, because that makes more sense with this theory. Here are areas of the waves that will be constructive interference. With the purple, I'll show you guys there and there. That's an area of destructive interference because you have the exact opposite part of the wave hitting at that spot. Another example may be like here and here. That would be a destructive area of this wave. And here at the end, that would be a destructive interference of this wave. So what that actually looks like, if you actually drew the picture of these guys together, it would actually look like something like this. And actually, it will be more condensed. So it would actually be something more like. It would actually be something more like this, little pockets. One wavelength, three wavelengths. You would actually get little pockets like this. I am going to post two things in the chat right now. The first one is a video, and I would like to watch that video together with you guys so that you can see something really cool. Let me just put the caps on these markers so it doesn't dry up. Okay. And if you guys in this video link, if you could turn, how you can open up the volume mix or whatever, open up the video, but mute it and just listen to my voice so I can tell you a particular part of this video that I want to focus on. So once again, if you guys go to about the, what is it? If you guys go to the 20-second clip, the 20-second mark on this video clip, you're going to see a stream of water, and it says in the video that they're producing a 24 hertz sine wave. Now, what that means is that the speaker is going to produce a wave, a sound wave, that operates at 24 hertz. And we know that that means the frequency. And there's something really cool that's going to happen if you guys play the clip. The video camera that is actually recording this is also operating at 24 hertz. So what that means is that the video camera takes a picture 24 times in 1 second, and it happens to match perfectly with the sound coming from the speaker. So if you watch the video clip, you will see the water appear like it's stationary. In real life, it's actually not stationary. But what's happening is every time the camera takes a picture, the water is at the same part in its moving track. So if he puts his finger somewhere where there's no water, his finger would actually get wet. And it looks like it's magic, but it's not really. It's science. So I'll give you guys a second to kind of look at that. It's a really cool video. And you could see him turning the speaker on and off again. Okay. So once you guys saw a little bit of that clip, which is really cool, you should skip ahead to the 1 minute and 5 second part. So what's going to be special about this is that the camera is still operating at 24 hertz, but he's going to change the frequency of the water to 25 hertz. Now, what is actually happening there is the same thing we just showed you guys in this picture, except instead of two waves, it's going to be the camera and the actual sound wave in the water. They're not going to be 100% in sync, but there are times when it will be in sync, and there are times when they'll be out of sync. So you're going to get a pattern that looks like it's moving very, very, very slow. And that starts at the 106 mark. So if you guys want to go to the 106 mark, you'll see what I'm talking about. So once again, at the 106 mark, he changes the frequency of the sound, and now it looks like the water is spitting out, but it's going in a very small zigzag. Once again, in real life, that spigot is going 25 times a second, but the camera is picking up every 24 times a second. So there are times when the spigot is at the very top position and times when the spigot is at the very bottom position. This is what we call a beat. So now it looks like the wave is actually moving. At the 145 mark, he does it backwards. he has the camera going at 24 hertz a second, and the sound wave going at 23 hertz a second. So it's backwards for our eyes. It looks like the water's going up into the air. But in real life, once again, it's just the camera taking a picture at a different synchronization point than the actual water. And that visualization of the water going upstream is nothing more than constructive and destructive interference happening at the same time. And that's how you get that really cool effect. I have another website to show you guys. This here is a link to an online simulator. This simulator has a lot going on with it. You need to make sure if you're going to play with this that you see it the right way. If you full screen it, you can adjust a lot of different things on the two graphs, graph 1 and graph 2. You could do, the frequency, the wavelength, the velocity, the amplitude. So if I were you guys, I would try to play this up and match the two waves together. Match 1 and 2. So you need to use your mouse and adjust the dials on the sliders, and I want you to match 1 and 2 up perfectly. The key here is you got to do the velocity first. So set the velocities to match each other, and then you can get the frequency to match the other frequency. The wavelength will automatically change. And you should also adjust the amplitude just for measurement purposes to be the same. And I want you to make sure that those are the same. And I'm going to give you guys a moment to do that if you guys are still playing along with me. You don't have to change any of the settings on the bottom, the sine versus triangle, transverse, longitudinal. You don't have to change any of those because this is a visualization of beats. So if you guys would be so kind, if you could just change the red and the red to match the blue, use the velocity first, and then go from there. And then you will see the purple one is the interference, if you would. And if they are lined up correctly, you should see identical lines there. So I'll give you guys a moment to play with that, get those settings up and running. All right. So at this point, hopefully, you could always pause this video during playback. That's perfectly fine. What I would like you to do at this point is not adjust the speed of the wave. I want to adjust the frequency, and I'm going to make it go a full hertz bigger. So it's going to take some finagling. This mouse is very sensitive. And I want you to literally make it a full hertz bigger. So if the red one is, let's say, for example, 1 hertz for you, make the blue one 2 hertz. And I know it's really difficult with this mouse feature, but it looks really the best if you can get it to really line up correctly. And that's the funny thing. It doesn't necessarily refer to beats in music. It's a common misconception that some science terms actually relate to music terms. This is actually more of if you're in key or not. So you know how if you're strumming and you can just, before you actually play music, you kind of play around and then you tighten the string and you play around again, you tighten the string to see if it's in key. That's actually what people are measuring in their ears. Professional piano tuners and people like that, they would use, when they're training, a frequency generator or frequency oscilloscope, it's called, to measure the frequencies of the keys. So, for example, an A key is 440 hertz. So, if you press the A key, you should see on the screen a wave that's 440 hertz. What actually happens in real life, let's say your key's a little bit off and it's operating at 437 hertz. If you're playing in a giant group and your piano is just a little bit different, something will sound funky in the music when you play it all together. So there are trained guitarists, musicians that can actually hear this when it's not right. They just have a sense of knowing when it's actually right or not. So a beat is actually just a difference in the key, essentially. And once again, if you see the simulator and you see the packet together, there are areas where it's big and there are areas where it's small. And that is what actually happens with the beats. Play around with it. You can get some really cool little packets of waves. So for example, I'm just playing around and I have my frequency. I have my wavelength. No, my velocity to 0.2. And then I have one wave that has a 0.11 wavelength, and then another wave that has a 0.10 wavelength, and that purple wave is little packets. That once again, when you hear things out loud, that would actually sound not exactly pleasant. You would feel like there's something off about it. There is another simulator that I have for you guys. I just got to find it, that you can physically hear that difference. So let me see if I could find it again. Here it is. Okay. So I'm going to attach this guy in. Actually, I'm going to play this first because it should come up over my speakers. No, you're not mixing up rhythm and beats. Beats, when you're in elementary school, you're keeping the beat, right? That's what you're taught in elementary school. But if you actually think about it, if I'm going at this rhythm, at this frequency, and you're going at this frequency, yes, the beat is off because you're not in sync. There are going to be areas where your hand is coinciding with the other person's hand, and then their area is going to be completely off sync. So when it comes to beats in elementary school, when you're taught about it, 3, 4, 5, 6, 7, 8, and someone else is 1, 2, 3, 4. Eventually, those hands are going to match up, and you're going to get these ideas of the beats. I'm going to be quiet for a second, and I'm going to play a sound for you folks. So I apologize if it's going to sound a little loud on the speakers, but this is actually going to sound really cool. So hopefully this loads in a second, and I'll load this link up too, but I want you guys to hear the difference in what these waves actually sound like. So I'm going to get rid of that. Okay. So once again, I'm sorry about your volume. It may appear a little bit loud. So just bear with me. It's loading right now. All right. So I'm going to make a sound, and the sound is going to be monotone, meaning you're just going to hear a sound, nothing special about it. I guess my speakers don't work and I can't scream at the same time. All right, I'm just going to share this with you guys. Here's another one, and once again, this one actually has a speaker to it. I don't know if you guys can mute me and listen to the sound, or if you can listen to both at the same time, but I want you to play in the simulator, and I want you to tap the tuning forks at 100 hertz each. I want you guys to see what it looks like and sounds like at 100 hertz each one. Once you get that, I want you to then change the frequency of one tuning fork by 1 hertz. So have 100 and 101 hertz. And I want you to see and hear what that sounds like. And so I'm going to give you guys a minute to play around with that. Just have fun with that simulator. I'm going to be here for another moment or two. Have fun with that simulator. Play around with it. I want you to hear the difference and see the difference in your eyeballs about what the waves actually do when they're out of sync with each other. So I'm going to just take a drink of coffee and just play around with that a little bit. Remember, change the amplitude, change the frequency every so often and see the pattern that develops. Okay. So that should be some time for you guys to once again play around with this and actually see a difference and stuff. You can zoom in and out on the wave. That's what the little blue and gray sliding bar is all about. So here's the cool thing about beats. And once again, now that you guys are actually visually seeing it, here's how you can figure something out. Let's say the frequency of this wave is 10 hertz. And let's say the frequency of this purple one, a little bit different, is 12 hertz. Let's just say this is just a rough estimate. So we have 10 hertz and 12 hertz. If these two waves interfere with each other, the resultant frequency would actually be, the frequency of the beat would actually be 2 hertz. And I got that just from subtracting the one frequency minus the other one. And it would actually be 2 hertz. So you would hear on that app, you would hear 2 high and low spots every second. That's what you're actually hearing once again when things are not tuned correctly. So you guys can do calculations based upon this idea. Okay, if this wave is going at this frequency, this one's going at this frequency, this would be the resulting wave. How fast does that travel? V equals F lambda. The medium is going to be the same between the both of them. So you can figure out the wavelength of the beat. And those are the types of questions you may see about beats upcoming. Does anybody have any questions at all at this point in time? I know Kevin asked a question. Krishi and Akshay, I hope you're still in here. If you guys have questions, don't be afraid to ask. But the cool thing about doing this is that you guys have the links to the interactive, so you could always play on your own as you see fit. But do you guys have any questions at all about this idea of the interference not just being amplitude based, but it can also be frequency based, and your results can be little packets of waves. So I'll give you guys a second. Once again, does anyone have any questions at this point about how beats work, or anything in general that you guys have a question about? Yeah, of course. That's fine. Which yeah, I'll be happy to. I'm just going to pull it up on my screen. Okay. So, Crescian, for anyone in general, because of the nature of the AP problems and stuff like that, just tell me which assignment it is and which problem number it is. I can't show you guys actual problem stuff. I could just talk about what the problem is, just because I can't on the webcam hold up a solution problem. We're just gonna have to talk it out. So whatever assignment it is and whatever problem it is, just let me know so we can look at it together online, and we'll just go through the answers and discuss why each one is not there. Sorry. Okay, AP Classroom Unit 10. Is it from the multiple choice part 1 or multiple choice part 2? Okay, I'm just having issues getting onto the website. Just bear with me a second. me try over here. I just can't type today. That's the issue. Sorry, guys. Just give me a second. I'm just pulling up the problems. And Krishi, which problem did you have from this? So I can get that ready too. All right, I'm almost there, guys. 15. Is that from B or A? Like B was the part that I assigned on Friday. Okay, Krishi, I'm going to just look for it. I'm going to get Kevin's first because I know exactly where that one is, and I'll find yours too. As soon as the computer loads. All right. All right, Krishi, I think I found yours anyway. Let me just pull up number 10, and then I'll do 15. All right. Kevin, just to confirm, the one you have, question 10 on part B, there was a tube with a sound wave generator. Is that the correct one? A tube with a sound wave generator above it with like water and air? Okay. A group of speed of sound in the tube. Oh, okay. So once again, this is for the problems you guys had for Friday online. It was problem number 10 that we had online. Okay. Remember, in this case, it says there's a tube that's open, but if there's a water level, this will actually be a node, and this region would be an antinode. Okay? So if you think about a standing wave, when you have an antinode because of the open part and a node because of the closed part, you're going to get a wave a standing wave that looks like a cone. And if you guys remember what we talked about in class, this picture of the standing wave is only 1/4 of a wavelength, because here you have half an antinode and one wavelength is 2 antinodes. So in this picture, you only are 1/4 of the way there. That is why the correct answer would be A, because the idea that you're only seeing 1/4 of the wave, and their answer is based upon that length. So that is why the question would be A, or the answer would be A. Is that okay, Kevin? Okay. Krishi, I found your problem. Let me just get the other mouse. Okay. And Krishi, just to confirm, yours was a transverse wave with a bunch of dots. And they're asking about a group of students with a slow-mo camera. Is that the correct one that you're thinking of? Krishi, is that the one where they're talking about, the picture and they want to know what things can be measured? Is that the correct one for you? Okay. So here, the key things are the axes. If you look at the vertical axis, it says centimeters of the vertical displacement. That's the amplitude. That's the height of it. And in this case, they also give you the time at the different points. So once again, whenever you see vertical displacement in centimeters, that's the definition of amplitude. We can get the amplitude from that. So the amplitude is definitely one of the two correct answers. Once again, because the y-axis describes exactly what the amplitude actually is. The other question, I understand the debate here. The thing is, they give you time. So we can look at this picture and figure out how much time it takes for a wave to make. When you look at the options that are available left, we have speed, wavelength, and frequency. We can't figure out the wavelength because the unit is seconds. It's not meters. It doesn't tell you how far apart they are. They tell you how much time that is. So it definitely won't be B. And once again, because of the units in the axis, it won't be A, because then we're looking for meters per second. And we wouldn't see a wave like that. We would actually see a straight line, because that would actually be consistent. The answer would be frequency. Once again, if we can actually look at the units, we could figure out that they're giving us time, and then we know the correlation between the period, aka time, and frequency. So we could just do a quick calculation and say, oh, if the time is 0.75 seconds, the frequency would be 1 over 0.75. So that's why frequency and amplitude would be the correct answers. Okay. Oop, hold on 2 seconds. Hi, thank you guys very much for that. So at this point in time, we're going to wrap things up. I do have another stream to do shortly. Here's how we're going to proceed. Yep. I have my bagel right here for you, Krishi. Here's the deal. At this point in time, I am going to open up the free response questions on AP Classroom. I am not going to stream tomorrow with you guys. I will give you a 2-hour block on Wednesday. Once again, I am not going to stream tomorrow, but I will do a 2-hour block with you guys on Wednesday to discuss any problems, multiple choice or open-ended, or I'm sorry, I call it open-ended, free response for you guys. So once again, after this stream, I am going to post the free response questions. And once again, on Wednesday, I will give you guys a 2-hour block. Krishi, what works the best for you? Do you guys like the morning or do you want to do something in the afternoon? Yeah, I will do live stream for 2 hours on Wednesday. What time? That's up. What do you guys think? And since you're one of the only people here, I'm going to very much listen to you. No live stream Tuesday. We'll live stream on Wednesday for an extended time. Of course, the afternoon works. Krishi, are you okay with that? Doing an afternoon live stream? Okay. So as of now, let's do this. 12 o'clock on Wednesday. We'll do a 2-hour stream, and you guys can answer me any questions you want, free response or open-ended. 12 o'clock sound okay? 2 hours, Wednesday. No, apparently I'm not the only teachers doing live streams. I think I'm the only one using YouTube. Some teachers are using other means, but we're trying. So, all right, if that's the case, guys, have a good morning. Krishi, enjoy your breakfast. And we'll touch base again on Wednesday. And keep an eye out on Google Classroom just in case. But yes, you will see the problems opened up later today. All right. Yes, enjoy your day. Have a good one, folks.